So now let's look at Chapter 8, ion implantation. So in short, in the ion implantation process, so a gas is ionized and ions are accelerated by the high electrical field and injected into the target wafer to 100 nanometer depth. So the typical ion implantation parameters, so the ions are dopant ions. The dose is 10 to the power 11 to 10 to the power 18. So dose, the unit for the dose, so the unit for the dose is atoms per square centimeter. We know that for the dopant, the concentration is atom per cubic centimeter. So the relationship is this one. So the dose is given by the integration of the dopant concentration. So we can do some rough estimation. For example, if for this dose, if the depth implanted is 1 micrometer, so this is already pretty deep. So 1 micrometer is given by 10 to minus 4 centimeter. Then you can see that the concentration have order of 10 to the power 22 per cubic centimeter. So this is the concentration. So the concentration is given by the dose, the depth. But this is very rough. In reality, so we have the Gaussian distribution. But roughly, if we do the dose over depth rather than the Gaussian distribution, so we get this number. You can see this is very, very high number. So we know that for the silicon atoms, so the number density is given by 5 times 10 to the power 22. So you can see, so the ion implantation dose can be much higher, can be even comparable to the silicon atoms concentration. So there's very, very high concentration. So the ion energy is 1 to 400 kilo electron volt. It's very uniform and reproducible. The room temperature, the ion flux is given by 10 to the power 12 to 10 to the power 14 ions per square centimeter per second. So the idea was proposed by Shockley. Now he is one of the three persons who invented the transistor in 1947 at the Biolab. This idea came out in 1954, but it became mass production only after late 1970s. So before ion implantation, the doping is done by the diffusion doping, as we learned from Chapter 7. This includes the diffusion from the gas source above the surface or predominated chemical source on the wafer surface. But the diffusion lacks the flexibility and the control needed for the CMOS process, so the ion implantation gained popularity. So modern ion implanters were originally developed from the particle accelerator technology, and also the implantation is always followed by the thermal activation process. Now this thermal activation has two purposes. One is to activate the dopant atoms. The second one is to repair the lattice damage. For the advantage of ion implantation, so first we have precise dose control. So when we have the ions, so we have the current. So the current can be measured precisely, and also we can measure the current density. Then the dose is given by the current density times time. So dose equal to current density times time. So J equal to current divided by area. Secondly, if we have a low current density of 1 nanoampere per square centimeter, then with the minimum required time of 10 seconds, then the dose can be as low as 10 to the power 11 per square centimeter. So this one is easy to get. So 1 nanoampere times 10 seconds. So this will give you about 10 to the power 11 per square centimeter. So this one needs to be divided by the charge Q. The charge of the electron. This gives you the dose. 1 nanoampere 10 seconds divided by the charge of the electron gives you the dose. This gives you the number of about 10 to the power 11. On the contrary, in the diffusion process, the value less than 5 10 to the power 13 is not easy to achieve, because in the high temperature diffusion process, as we learned from Chapter 7, the dopant gets into the top surface and to reach the solubility very fast. And also for the ion implantation, we can have the high dose introduction is not limited to the solid solubility as we see in Chapter 7. for the case of the diffusion doping. And also it's very uniform. It's 1% uniformity across a 12-inch wafer. But there is less dopant lateral diffusion. For example, this one here is diffusion and drop-in. You can see we have big lateral diffusion. For the ion implantation, the amount of the lateral diffusion is smaller. It's done in a high vacuum and very clean process, and we can have precise dose control and also control of the profile. For example, you see the profile depend on the ion energy, and you can do the different several ion energies to give you a combination of different profiles. But for the case of the diffusion drop-in, the profile is very unique. Just it's always the peak concentration always near the surface. But for ion implantation, you can see the peak coming below the surface. We have more control over the profile. And also it's a room temperature process, so we can have the different mask materials. For example, we can use photoresist, oxide, polysilicon, metal, all the material can be used as a mask. For the case of the diffusion doping, normally we just use oxide as the mask for the diffusion doping. So it's less sensitive to the surface cleaning process because this was room temperature, so some chunks on the surface will not hurt the sample too much. It is very fast. It can be very fast. For example, a 6-inch wafer can take 6 seconds for a moderate dose. Because this room temperature, there is no heating up and cooling down process. And we can have complex profiles by multi-energy implant. So this is the same as what we have see here. So the profile can be controlled because we can have the multiple energy and multiple doses to give the profile as we want. The disadvantage, first, the equipment is very expensive, like $1 million. This is about 10 times that of the diffusion, the furnace doping by the diffusion. At high dose values, the throughput is less than the diffusion. Because the thermal diffusion, we can put the wafer like this. We can put hundreds of wafers, and do the doping at the same time. For the ion implantation, the wafer needs to be put like this, obviously. It needs to be set by side like this. Another disadvantage is ion damage, and not all the damage can be repaired by the annealing process. A very shallow doping is difficult or impossible because ion needs some energy to implant into the silicon, and the mask material can be knocked into the wafer to create some unwanted impurities. But this is the dose energy application space. For example, we have talked about this is the polysilicon. This for the gate. For the gate needs to be metal, needs to be very conductive. So we have very high dose. And moderate energy. So this is the source drain contact. For the contact, we need small contact resistance. So we also need high doping. And extension. This is also called, as we learn from chapter 2, laterally dope the drain. So this is the smaller doping. And this is the higher energy give you deeper doping. For example, this is the CCD camera. So CCD camera is used for the camera for the cell phone, but nowadays mostly people use a CMOS imager. People use CMOS imager for the cell phone. So in the old times, people use CCD more than the CMOS. The CCD has better performance than CMOS imager, but CCD is more expensive. Another application, as you see here, this is the SOI wafers. Is that here? So this is the silicon on insulator. So this is for the wafer bonding silicon on insulator. This is silicon on insulator called SOI. So now we talk about SOI wafer. So SOI wafer means silicon on insulator. So so we have the silicon. So we have the silicon oxide, and then we have the substrate. The substrate is also silicon. So this is the SOI, silicon on insulator. So one way to make the SOI wafer is called a CMOS, separation by implantation of oxygen. In this case, so we do the oxygen, we do a very, very high dose. You see, 10 to the power 18. 10 to the power 18. So the peak concentration here will be 10 to the power 22, maybe even bigger than this. So this is already close to the atom number of the silicon. The silicon we know, as we said, 10 to the power 22 atoms per square centimeter. So this is very high dose. Then we do a linear process. Then oxygen will react with silicon to form the silicon oxide. So we have this silicon oxide layer here. And we want a thicker. We want to increase the silicon thickness. We can do the epitaxial layer to grow more silicon. Now this one, the actual wafer provides better performance for the high-speed circuits than conventional wafers. It's also good for the isolation. So in chapter 2, we talk about isolation between the CMOS in the CMOS. In the CMOS, so we have the PMOS and we have NMOS, and in the between. So what we do, one way to do it is to do the thermal oxidation. We grow a thick oxide layer to isolate CMOS and NMOS, to isolate the PMOS and NMOS. But even in this case, there's still it's possible for the current, for the charge carrier to flow from one set to the other set. That means the PMOS and NMOS, they are not fully isolated. But when we have the SOI wafer like this, so we can do something. So this is the silicon oxide, silicon substrate. And we can have this part. This can be NMOS, this is PMOS. So the area in between, this area here is etched away. So in this case, you can see the NMOS and the PMOS, they are fully isolated. So this is good. But the problem is this oxide layer. So we know that, so the heat dissipation is a big problem for the CMOS when we have higher and higher density CMOS. So, but when we have this silicon oxide, so silicon oxide is a poor thermal conductor. So the heat is not easy for the heat to dissipate through the substrate. So this limits the application. So the heat dissipation limits the application of the SOI wafer for the CMOS application. Another limit is the cost. A normal wafer may cost $20. SOI wafer costs $200. So the SOI wafer by this CMOS process has better yield, but more expensive than the wafer bonding and the CMP process. This is what we'll talk about in the next slide. So 400 nanometer battery oxide requires a very high dose. With very high dose, this we know the very high dose, but this is a slow process. Another way to do the SOI wafer is called a smart cut. So in this case, so we do the hydrogen implantation. This is also very high dose. We have this hydrogen here. Then we have this called handle wafer with thermal oxide. This is the thermal oxide on top of the handle wafer. Then we do the wafer bonding. Wafer bonding. Then we do a thermal or mechanical cleavage. So when the hydrogen ion has very high density, it becomes hydrogen gas. So we have some kind of a bubble. And you form some bubble at the interface, then it's easy to break. So this is the way for the smart cut. So here we talk about the wafer bonding and the CMP. So this is the most popular way to make the SOI wafers. Wafer bonding and the chemical mechanical polishing. Chemical mechanical polishing. In this case, so we do the wafer bonding, then this part here is polished away by the CMP process. This way we can have the thickness can be any number. So this one can be the thickness can be the top layer. Silicon oxide, silicon. So the thickness can be any value because this can be, for example, 100 micrometer or 10 micrometer. But for the ion implantation, it's always less than 1 micrometer. So the limit for this for this method is the thickness variation. The thickness variation for the polishing process give about plus minus 0.5 micrometer. But this can be too high value for some applications. So besides the CMOS, another more popular application for the SOI wafer is MEMS. For example, it's widely used for the gas sensor, pressure sensor, and also used for the microphone. This is MEMS microphone. For all of them, they are all used as one wafer. So here we have the silicon oxide here, and here we have silicon here and the silicon here. So the advantage for the actual wafer is that we can pattern the backside. For example, we can etch away the silicon, we etch, and it will be stopped as the oxide wafer. Then we pattern the front side, we etch. It also stopped as the oxide. That means the patterning of the backside and the patterning of the front side can be isolated by this silicon oxide wafer, by this silicon oxide layer. And that's why the SOI wafer is very popularly used for the MEMS. So now we look at the tools. So this is the overview of the ion implanter. So first, we have the ion source. Then we have the mass spectrometer. It's also called analyzing magnet. So this one select the desired impurity ions and to go through the following process. So then we have this accelerator. This one is very high voltage, give you the ion energy needed. Then we have the scanning system. We have the actually by scan to scan the ion across the wafer. So we have the Faraday cup. This one measure the dose. Now we have the neutral. It's called the neutral trap. This one gets rid of the neutral particles. Now we will look at each of them one by one. So the first one is the ion source. There are two types of the ion source. The first one is the plasma source. So this is obvious. We know in the plasma there are plenty of ions. Then we use this extraction voltage to extract the ions to come out. The second one is called no plasma. It's called the Newton type gaseous sources. In this case, we have a hot filament. A hot filament will emit electrons. Electrons come out. Then we have the gas here. For example, we have this gas, pH, phosphine gas. So when the electron collides with the gas molecules, it will create ions. For example, the phosphorus ions. Then they are attracted. Then we have the extraction after that, so the ions will come out. And this is the ion source. So now let's look at how to look at this one, analyzing magnet. So how to select different ions. So what we do, we use the magnetic field. So we have the north pole and the south pole. So we have the magnet. So we know that when the particle moves in the magnet, it will have the magnetic field. It will move in a circular way. So the radius is given by this formula here. So we know that mv squared over r equal to qvb. This is the Lorentz force. The speed is given by 2 energy divided by m square root. Energy, we know that equal to qv. This energy equal to qv. So in the end, we have r equal to this value here. You can see the r depends on the mass to charge ratio. The mass to charge ratio is given by this formula here. So different mass to charge ratio give you a different r. Then we can have a small opening here. Only this one can come through. So the dopant gas contains the desired species. For example, we use BF3 or phosphine or those gases. If we use solid or liquid source, they need to be heated to vaporize first. So plasma provides positive ions. We can have different ions. For this case, we have the BF3 gas spectrum. We have a boron, fluorine, many different types. So what we need is the boron. In this case, we need this one. We need boron 11. So only the boron 11 can come out. But this one is for the boron we have 2 isotopes. The boron 11 is about 80%, and boron 10, this one has 20%. So this is how to select the species. Next is the ion acceleration. This one we just use very high electrical field, but we do not do like a parallel plate like this, because this, if it is like this, the field, you can imagine the field may be, the field may not be uniform. So what do we do? We divide the voltage into different sections. So we have, in this case, we have 1, 2, 3, 4, 5, 6. We have 6 metal plate. So we have the 100 kilo electron volt high voltage here. We have very big resistor here. So they are the same resistance. Then the voltage drop will be the same. You can see we have 20 kV drop, 20 kV drop here, and 20 drop here, and 20 drop here. Then this is the potential between the each of the plate. So this way we get more uniform electrical field for the ion to be accelerated. So the final energy of the ion is given by the charge times extraction voltage. This is right here. Extraction voltage plus the acceleration voltage. Acceleration voltage. For example, this can be 30, this can be 70 to give 100 kilo electron volt. So now let's look at the neutral trap. So there may be ions that collide with other ions in the beam. Then they may undergo charge exchange. For example, the 1 bar ion. The 1 bar ion, they collide with another bar ion to form the boron, to form something like this. This one is the neutral. This is the neutral, not charged. Other neutrals, they are highly undesirable because they will not be deflected in the electrostatic, antioxidation, and scanning mechanisms. To get rid of the neutral, so we use this. What do we do? We apply an electrical field. For the neutral, it will go straight. For the ions, for the boron ions, it will be bended. It will be bended. So when they are bended, they will go downstream to go to the wafer. So this is how the neutral trap works. So this is the beam scanning, electrostatic scanning. So here we have the field, this direction, y direction, and we also have the field along the x direction. So when we scan the field like this, then the ion beam will scan on the wafer surface like this. So in the end, we get uniform doping across the wafer. So the frequency is about 100 Hz. So you can imagine if we have the neutral, but this one will not scan like this. So it may hit this spot, and it will not move around. That's why we need to get rid of the neutrals. Because the neutral will not be scanned like this. It will be implanted into one single spot. But this will be very bad. Another way is called a mechanical scanning. For the mechanical scanning, we can have 15 to 20 wafers per disk. So we can have put many wafers, and we have very high throughput because we can have high current. This one we have 20 milliampere. For this electrostatic scanning, the current is less than 1 milliampere. So in this case, the ion beam is stationary. So the ion beam is fixed. Do not move. The ion beam is fixed, no movement. But the wafer, you see the wafers, they scan. We do the rotation, rotate, and also we do the translational wafer movement. If the rotation and the translational wafer movement is well designed, we get uniform doping across all the wafers. But this one, you see, is very expensive. It can do 60 wafers per hour. The last one is the dose measurement. So what do we do? So this is the wafer holder. So we put a small thing called a Faraday cap. So in this case, this may be the size here, maybe 5 millimeter, very, very small. We have small opening here. So then we have the ion come here. There may be some secondary electrons. But here we have this positive barriers. So the positive barriers, so the electrons will be trapped. To the side wall. So in the end, there will be no charge So all the charges will be collected by this cap. No charge will no ions or no electrons can exit. So all the charge will be collected. This way, if we know the charge, we know the current, and if we know the cap area, we know the current density. Current density times the time give you the dose. So this is how you get the dose by using this Faraday cap. So effectively, this one measures the charge trapped in the cap. So now let's look at the dopant distribution profile. For the first order approximation for the random process, for the statistical random process. So normally we have this Gaussian distribution as the first order approximation. So this is the Gaussian distribution. So the projected range is here. This is the depth. This is RP. RP is projected range. This is a function of ion energy and mass and atomic number of the impurity as well as the target material. Then we have this delta RP. So this is delta RP here. From here to here. This is the delta RP. Here. Now this delta RP called the threshold is also called the standard deviation. You can see delta RP is here. RP is here. Delta RP is here. So MP is the peak concentration as the RP actually equal to RP. So the dose is given by, if we do the integration, we get the dose. The dose dx is given by this value here. But this is not difficult because we know that E minus x squared dx minus infinity to plus infinity given to square root of pi. This way we do the integration, we get the dose. So in the end, the dopant concentration given by MP times this one. If we put the Q and MP here, we have this one here. So this is the profile. So if you know the RP and the delta RP and the dose, you know the profile. So here is the depth. So this one is RP. So you can see the boron is light. This is the energy. The boron is light compared to the phosphorus and antimony and arsenate. We get deeper. Boron gets deeper than other dopants. Now this is the standard deviation of delta RP. Again, the boron is the highest than other dopants. So this is energy here. So normally, typically, roughly, delta RP is given by this formula. So it is related to the RP. So the higher the RP, the higher the delta RP. For example, if the mass is roughly the same, ion and the target is roughly the same, but this one will give, this is 1/3 RP. So roughly you can see, delta RP can be 1/3 RP if the mass they're roughly the same. And now we have one example here. So here in this case, so we have the phosphorus. So we know that silicon. So there's sodium, magnesium, aluminum, silicon, phosphorus. You can see silicon is 14, phosphorus is 15. So they are very close. So this one, 14 and 15, atomic number. This is atomic number. So this one, Mi and Mt, this will be very close. So then we have this, roughly, we have this relationship. So the phosphorus with energy 100 kilo-electron-volt is implanted into the silicon wafer. So what should be the implanted dose if the peak concentration is of 10 to the power 70 is desired? So here, for the 100 keV, we can find out RP and delta RP. So you can see here, so phosphorus 100 keV, you get the RP, and the 100 keV for phosphorus, you get the delta RP. Then this value is given by 0.12 and 0.045. So you can see roughly 1/3 RP. 1/3, as you see here, so 1/3 RP. So when the mass, they are similar. Then the charge, the dopant, the dose is given by. So if you know the delta RP and you know the peak, you find out you know the Q. It's given by this formula here, and you get a different number. So what length of time is required to implant this dose into a 200 millimeter wafer using 2 microampere beam current with single ionized phosphorus? So the formula is given back here. The time equals to charge divided by current. Divided by current. The charge, the total charge is given by the M. M for the single ionized phosphorus, M equals to 1. So M equals to 1. This is the charge of electron here. A is the area here, pi r square, and the dose is given back here per area. The current is 2 microampere. It gives you 24 seconds. Thank you.